Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to Technogener. In this lecture, I will discuss about the design and the basic parameters of the wind turbine. So, as you see in the figure, you will understand that the size or the height of the wind turbine is based on the turbulence or the objects nearby it. Because if there are objects like home or trees or buildings nearby it, then there is a chance to have turbulence in the wind, and the chances to produce electricity is not uniform, and then it will create disturbance in the national grid. So there are different parameters in the wind turbine, like the height of the tower, then the size of the blade, then the temperature, then the pressure, and other parameters. So in order to design the wind turbine, we have to take consideration of all the parameters. So let's start. So as you know that there are the wind, wind is basically the air in motion, and a mass within which is in motion has a kinetic energy, and the basic formula for the kinetic energy is half mv square. So the m is basically the mass, and v is the velocity of it. So in order to measure the power or the energy in that kinetic energy, then we have to multiply it with the time. So the energy per unit time is basically the power. So if we divide the kinetic energy divided by the time, then it will be the power, and in the basic formula would be half m mass over time into v square. While the mass over time is basically represented by rho a into velocity, where the rho is basically the air density area, a is basically the area, and v is the velocity. So if we put the value of m mass per unit time in the formula, which is this one, mass mv square, then the overall formula will be rho a into velocity cube. While the area of the wind turbine is normally pi r square, and if we convert, change the area with the diameter, then it will be pi by 4 d square. So if we put the value of the area in this formula, then the formula will be basically rho v cube into pi divided by 8. So this is basically the power and the speed graph of the wind. If you see that I will take the pointer. If you see that the when the wind increases, the output of the wind turbine increases in an exponential way, because the relationship between the speed and the power is basically the cube. So there is an exponential increase in the power. So this, if you see, then this is the wind speed and this is the power. Initially both are zero, then the wind speed gradually increase, and so is the power. And when after that, when the wind speed increases, the power is basically the cube function of the velocity. So the velocity or the output energy increase drastically. So the second type of the wind turbine, which is the vertical axis of the wind turbine, then the area of the wind turbine would be 2 by 3 d over d into h, and the d is basically the turbine the diameter, and h is basically the height of the turbine. So let's see, this is an example. You will understand how we can convert the wind speed into energy. If we this is basically, if you see the statement, the compare the energy at 15 degrees. So the temperature is 15 degree, 1 atmospheric pressure, and contained 1 meter scale of the following wind regime. So we need to calculate the output of the wind energy. There are two different cases. One is we have 100 hours and the speed of the wind is constant, that is 6 meter per second. The second one is we have 50 hours and the speed is 3 meter per second, and the second, for the second 50 hours, the speed is 9 meter per second. So these are the two different cases. So for the first case, we need to calculate the energy. So we have half rho A into V cube into time. So rho is basically the air density, and which is basically at 15 degree, it is 1.225, and area is given, and that area is basically 1 meter square. So if we put the value of the area, that is 1 meter square, and the speed or the velocity for the first case is basically 6 meter per second, and the time is basically 100 hours. So the overall electricity which is produced by the wind turbine is 13,230 watt hours. While if we take the second case, we have 50 hours at 3 meter per second and 50 hours at 9 meter per second. For the first case, we have half into rho. This is the value of the rho, and then the area, then the speed, and then the time. So the overall power which is produced is 827 watt hours. And for the second case, we have half, then we have rho into area into the speed, and now the speed is 9 meter per second into time. So the overall power which is produced is basically 22,326 watt. So if we add both the power, then the overall power will be 23,152. If we compare these two power, then you will understand that the power at 6 meter per second for 100 hours is 13,230, and the power for 100 hours, but for the first 50 hours it is 3 meter per second, and for the second 50 hours it is 9 meter per second. So the overall power which is generated is 23,152. So there is a huge difference between these two powers. So as you see that if we take the average of 3 and the 9, it is basically 6, and but the average power result, or 6 meter per second result, is basically 75% less than the power which is produced by the by individually in 5 hours. We in 50 hours we have 9 meter per second, and other 50 hours it is 3 meter per second. So the first parameter which is effective is basically the velocity of the wind, and the velocity of the wind can be we have to measure the velocity of the wind, and we cannot take the average of the wind. We have to calculate the power of each interval where the wind speed is constant. The second parameter which affect the output of the wind turbine is basically the temperature. The basic formula for the temperature is basically PV is equal to nRT, where P is basically the pressure and V is the volume, while N is basically the molecular weight, R is basically the ideal gas constant, and T is basically the temperature which is in Kelvin, that is basically degree centigrade plus 273. Uh, for the temperature change, we need to calculate the rho, and the rho is basically the air density, and rho is basically n into molecular weight into 10 is power minus 3 divided by the volume. And if we put these two values, this value and the previous formula value, this one, and combine these two values, then we have uh, P, that means rho is equal to P into molecular weight into 10 is power minus 3 divided by RT. So RT is basically come from the volume. We change the volume into RT divided by P. So the P goes up, and this is the basic formula. So for in this formula, we need to calculate molecular weight, and molecular weight is dependent on the air or molecular weight. So in the air, there the molecules which are basically nitrogen, and the quantity of nitrogen is basically 78.08%, and then we have oxygen, that is 20.95%. Then we have argon, that is 0.93%. Then we have carbon dioxide, which is 0.035%, and neon, which is 0.018%. So in order to calculate the molecular weight, we need to have the weight of these all these elements. Like nitrogen weight is 28.02, oxygen weight is 32, argon gas weight is 39.5, carbon dioxide is 44, and neon is 20.8. So when we multiply the percentage with the weight, then we have the molecular weight. Like 0.7802 is multiplied with the 28.08, and 28.08 comes from the nitrogen molecular weight. This one come from over here. And so this weight plus the weight of the 0.2095, that is percentage of this one multiplied by the weight of multiply the weight of the oxygen, and the oxygen weight is 32. So then we have organ weight, and then we have other material like neon and carbon dioxide weight. So the overall value is 28.96. This is the molecular weight of the air. So let's find the density of the air at 1 atmospheric fraction and 30 degrees centigrade. So the basic formula is pressure, which is 1 atmospheric pressure. Then we have 28.97, which is the molecular weight, into 10 to the power minus 3, divided by 8.2056 into 10 to the power minus 5, which is basically the R of the value, and then the temperature. So if we calculate these values, then the value of the rho is basically 1.165, which is different than the air density at 15 degrees centigrade, which is basically 1.225. So there is a difference between these two values, and this difference is due to the change in temperature. So this is basically the graph table representation. So at 15 degrees centigrade, the air density is basically 1.225, which is the normal standard testing condition. After that, if the temperature decreases or the temperature increases, then the air density changes with the change in the temperature. So if the air density changes, then the output of the wind turbine also changes. The third most important point is the altitude correction for the air density. So the altitude is basically the height of the height and the pressure. So if you see that there is an area, and which is basically Z, and if the altitude is changed, then it will be dz. So the dz is basically the change in the altitude, and change in altitude is basically the we can represent is pz plus dz. So this is the pressure which is created by the change in the altitude, and overall pressure which is created by the wind turbine. So for the change in pressure, we have Pz plus dz minus Pz. So this is basically the change in the new pressure and the previous pressure. So this change is basically G, rho, and dz. So if we move dz over there, then rho g is basically the change in pressure. So rho, the change in pressure divided by dg is equal to basically the formula of the pressure, that is g molecular weight into 10 to the power minus 3 divided by rt into pressure. So this is the basic formula. So if we want to check the change in the pressure, then it will be when we put all the values, like if you see this example, then we can simplify that like this one. We have 9.8 into 28.97, which is the molecular weight of the air, divided by 8.26, which is R, and the temperature. Then we have the atmospheric pressure in Pascal, and this is the whole change in pressure. This is basically the 0.185 into 10 to the power minus 4. So which is basically the solution, and the solution is basically P. The change in P or the pressure is basically the P naught into e raised power minus 1.185 into 10 to the minus 4. And this, if the atmospheric pressure is 1, then we can take that this coefficient, when it multiply with the pressure, then it will give the pressure of the overall pressure of the air. So we need to we if we have the value of the altitude, then we can calculate the output pressure. So there is an example: find the air density at 15 degrees centigrade to 188.15 Kelvin at an elevation of 2000 meters. So the altitude is basically 2000 meter, as in if we want to calculate it in feet, then it is 6562. Then find it assuming an air temperature is 5 degree at 2000 temperature. So there are two different. Point one is 15 degrees centigrade and the second one is 5 degrees centigrade. So the air density would be pressure into molecular weight into 10 to the minus 3 divided by R into T. So the pressure will be 0.789 atmosphere into 28.97 into 10 to the minus 3 divided by the value of the R multiplied by the temperature. So the air density would be this one. So if the temperature changes, then when we calculate the complete formula, then the air density is this one. So there is a difference between these two values because of the change in the temperature, and second because of the change in the altitude. So we can summarize that there are two different parameters which affect the air density. One is basically the pressure, and the second one is one is basically the temperature, and the second one is the altitude. So the basic formula of the air density is basically 1.225, which is basically the air density at 15 degrees centigrade. Then the combination of a coefficient k raised power t and the second coefficient k raised power a, and kt and ka are basically the two correction factor which are needed to resolve the value of the rho. So this is basic formula. You will understand that this is basically the altitude, this is the altitude in feet, this is the atmospheric pressure, and this is basically the ka due to the altitude. So find the power density watt per meter square in 10 meter per second wind at an elevation of 2000 meter and a temperature of 5 degree centigrade. So using kt and ki factor from table 6.1 and 6.2, this is basically 6.2, and this table is basically the 6.1. So we can calculate these values. So we need to calculate rho, and the rho is kt into ka. So at 5 degrees centigrade, then we can calculate, we can from the table we can get it is 1.04, and the second one is ka is 0.789 at 2000 meter, like this one. This is basically 2000 meter, and ka is basically 0.789. And then we if we take the temperature coefficient, that is at 5 degrees centigrade, it is this is the temperature coefficient, and it is the kt value is 1.04. So when we take these two values, one is 1.04 and the second one is 1.789, then we multiply, and the overall low air density is basically 1.00 kg per meter cube. And based on that air density, we can calculate half p into rho into v cube, because we do not have the value of the air. So pressure divided by area is basically this formula. That so the overall power is basically 500 watt per meter square based on the area. If the area increases, then the output power also increases. Now the third major point which affect the output of the wind turbine is basically the height. So initially we calculate the output with respect to the temperature, then we calculate the output with respect to the altitude, then we combine the output of the temperature and the altitude, and now we will focus on the height of the tower. So the height of the tower is basically the basic formula of the height of the tower is basically this one. Velocity velocity divided by the velocity at the reference height, then height over height divided by reference height raised to power alpha. So alpha is basically the friction coefficient, and alpha is given in the table. So there is another formula which is basically which is basically the natural log h over z and h naught over z. So this is the basic alpha coefficient, which is point. If the surface is smooth, hard ground, or calm water, then the alpha is 0.10. If there is tall grass or level ground, then it is 0.15. If there are high crops and shrubs, then it is zero point 0.2. If wooden or countryside or many trees, then it is 0.25. If there is a small town or shrubs, then it is zero point 0.3. If there is large city or tall building, then it is zero point 0.4. So the alpha continuously changing according to the surface. So the second is basically the Z, or the reference for the Z. If roughness is 0, then at the water surface it is 0.002. If it is an open area, then it is 0.03. If there is a farm, then it is zero point 0.4. If urban district, then it is zero point 0.4. And if there is a dense urban or forest, then it is 1.6. So this will create difference in the output. So this is the value of the output. This is the wind speed ratio, and this is the height of the tower. If the value of the alpha changes, then automatically the output power of the wind turbine also changes. So this is basically the graph between the power ratio and the height. So if the power ratio changes, then the output height of the power also changes. So this is an example. An anemometer mounted at 10 meter above the surface with the crop, hedge, and the shrubs shows a wind speed of 5 meter per second. Estimate the wind speed at a specific power in the wind at a height of 50 meter, assuming 15 degree centigrade and 1 atmospheric pressure. So based on the table 6.3, the friction coefficient of alpha from the ground and the ground with hedge and shrubs, it is zero point 0.2. If you see this one, this is basically the surface, and it will its value is zero point 0.2. So based on that value and reference velocity and reference height, then it will be 5 into 50 divided by 10. So this is basically the reference value. So the overall output velocity is 6.9, and based on this velocity, when we calculate the power, it is half rho v cube, and the rho is basically 1.225 into 6.9 raised to power 3. When we multiply it, so the output power is basically 201 watt per meter square. That turn out to be more than the 2.5 times as much power as 76.5 watt per meter square available in 10 meter. So this is the basic difference. So since the power in the wind varies as the cube of the wind speed, so we can rewrite to indicate the relative power of the height of the wind at a height h versus the power reference. So this is basically the power, which is the output power, and this is the reference power. So we can take the value in a value in this formation, and then the velocity of it. So the power is directly related to this one, velocity over reference velocity raised per 3, and similarly is basically the height over reference height raised per 3 alpha. So we can simplify the overall output of the wind turbine. So this is an example. If you see a wind turbine with the 30-meter rotor diameter is mounted with its hub at 50 meters above the ground surface, that is characterized by the shafts and the hedges. Estimate the ratio of the specific power in the wind at the highest point that a rotor blade tip reach to the lowest point it falls. So this is the 2 points. The highest point is basically at 65 meter, and the lowest point is basically at 35 meter, and the center is basically at 50. So the change in power is P over P naught is equal to H over H naught 3 raised to 3 alpha. That is height, maximum height is 65 and then minimum height is 35. So the difference will be 65 divided by 35 into 3 into raised by 3 into zero point 0.2. 0.2 is basically the alpha. So the overall output is 1.45. That means the wind speed at the top is 45% larger than the wind speed at the lowest point. Thank you, Jazakallah. Hopefully, you understand the basic concept and the designing of the wind turbine. If you have any query question, you can ask in the comment section. Jazakallah. Stay blessed. Allah Hafiz.